The Big Bang Theory is nearly perfect, except for one glaring problem. Where is all the lithium? The Big Bang Theory is our current best explanation for how our universe came to be and evolved to give us what we see around us today. But if you run the maths and get the theory to predict how much lithium there should be in the universe, it predicts over 3 times as much as we've observed with our telescopes. So is this just a case of we've been looking in the wrong place for all this lithium and we just haven't found it yet? Or is there something wrong with the predictions that the Big Bang Theory makes for what happened in the first 3 minutes of the universe's life? So in this video, we're going to dive into all this and chat first about how much lithium the Big Bang Theory predicts should be made, what's known as Big Bang nucleosynthesis. Then we'll chat about how and where we search for lithium in the universe with our telescopes. And finally, the possible solutions that we have to explain the lithium problem. So let's start with this Big Bang nucleosynthesis, i.e. what's found at the center of an atom. Specifically, it describes how in the moments between a second to 3 minutes into the universe's lifetime, how all the lightest elements on the periodic table are produce. So that's hydrogen with just 1 proton in its nucleus, in its center, or its heavy sibling deuterium with 1 proton and 1 neutron. Then also helium with 2 neutrons and 2 protons, and then lithium with 3 protons and 4 neutrons. Maybe even you might get a little bit of beryllium if you're lucky. So why does this process only give us the lightest elements in the universe? And why only in the first 3 minutes? Well, as the universe rapidly expanded, it also cooled down, spreading out its energy more, meaning that it wasn't hot enough for the heavier elements to form. Those would form later thanks to nuclear fusion happening in the cores of stars and thanks to runaway fusion during supernova. But how do we actually know all of this? Well, it's thanks to lots of different areas of physics coming together, from the standard model of particle physics to nuclear physics and cosmology. Now, the standard model is a theory describing all the fundamental subatomic particles known, along with 3 of the 4 fundamental forces: the electromagnetic force, the weak force, and strong interactions. It doesn't explain gravity though, that's left to Einstein's theory of general relativity. But it does include things like electrons that buzz around the centers of atoms, but also quarks that bind together to make the protons and neutrons that form the nuclei of atoms. So that means we have the physics to describe the particles themselves, but also how they're bound together in atoms thanks to the strong force. And we can describe what happens when those particles interact with other particles or decay to produce different particles. That's what's known as the weak force. We then also have our cosmological model of the universe that describes how it expanded to become the universe around us today. So what the predictions of Big Bang nucleosynthesis boil down to is predicting how particles will behave thanks to the strong force and the weak force in a rapidly expanding and cooling universe. So we know that when the universe is still very hot, you get a lot of weak force interactions with neutrons merging with neutrinos to make protons and electrons, but also protons merging with neutrinos to make neutrons and positrons. Once the universe is expanded enough so that it's cooled and reached a certain temperature, those reactions stop. You essentially freeze out the number of protons and neutrons so that you get a ratio of around about 6 protons for every neutron. As the universe expands and cools some more, it's then possible for the strong force to bind neutrons and protons together to make atomic nuclei. And it's then that you start to get a series of reactions occurring that forms all of these lightest atoms. And we know exactly which reactions take place because we've recreated them in labs here on Earth. We've studied them in great detail, so much so that we know how much energy is required for each one. But these reactions are a cycle of binding protons and neutrons together to make these atomic nuclei and then them decaying again. So the amount of each element that you end up making actually ends up depending on the ratio between the amount of normal matter you have in the universe and the number of protons you have in the universe. particles of light. Because photons, aka radiation, add more energy into this whole system, meaning you've got energy for different reactions. And it was only as recently as the 2000s that we were actually able to put a number on that ratio and measure it using the cosmic microwave background, the leftover echo of light from the Big Bang in the early days of the universe. With that ratio, we can then get an accurate prediction for how much of each of hydrogen, deuterium, helium, and lithium are made in the first few minutes of the universe's lifetime. What's known as the primordial universe. So you might often hear these referred to as primordial abundances of hydrogen or lithium. These are atoms that eventually go on to make the first stars in the universe a few 100 million years later. But these are just predictions of the theory. How do we know if these predictions are actually right? Which brings me to part 2. How and where do we search for lithium in the universe with our telescopes? Because it turns out, it's no surprise to anyone, it's quite tricky to measure the amount of primordial lithium in the universe. Unlike the amount of primordial deuterium, aka heavy hydrogen, because there are big clouds of hydrogen and deuterium gas hanging around space that get in the way of our observations of distant galaxies, and they leave a fingerprint on the light so that we know that it's there. And with that, we can measure not just how much deuterium there is, but also how much hydrogen there is as well, from the relative depth of the fingerprint that each atomic nuclei leaves on the light. That allows us to put a number on the ratio of the amount of primordial deuterium compared to primordial hydrogen. And so we can directly compare that with our predictions from Big Bang nucleosynthesis. That's what this plot shows. Both the prediction and the observed ratio agree. The same is true when we look for emission from helium in giant gas clouds in the early universe as well. We get a good agreement between our observations and predictions. The problem is that a lot less lithium is made in Big Bang nucleosynthesis compared to deuterium or helium, and there's just not enough in great enough densities in those gas clouds pervading space for us actually to be able to spot the tiny fingerprint that it would leave on the light. The only place we do see this is in the atmospheres of nearby stars in our own galaxy, where lithium absorbs a specific wavelength or energy of light in the star's spectrum, stealing away essentially a specific colour. That's the fingerprint that it leaves on the light. So what we do is we look for the oldest stars in our Milky Way galaxy, the ones that are over 13 billion years old, that formed relatively early in the universe's history, but won't necessarily be the very first stars made. And then we look at the amount or the ratio of lithium to hydrogen in those very old stars. We can trace how old a star is by how much iron it has in its atmosphere, iron only being made in runaway fusion during a supernova. So if you've got iron in a star's atmosphere, you know there have to have been a few generations of stars already lived, died, and gone supernova to actually even make enough iron in the universe for it to end up in the star's atmosphere. And it was in 1982 that Spite and Spite noticed that the lithium-hydrogen ratio didn't change with the iron-hydrogen ratio in the hottest, oldest stars in the Milky Way. It's what's become known as the Spite plateau. Because it didn't change with the iron over hydrogen ratio, aka the thing tracing the age of the star, it was interpreted as, okay, well, what we're directly measuring here is the primordial ratio of lithium to hydrogen, especially because the amount measured was very similar to the range that was predicted by the Big Bang nucleosynthesis model. However, 20 years later, when the measurements from the cosmic microwave background were made that would then narrow down those predictions because it gave us the normal matter to photon ratio, it was only then that the lithium problem became apparent, one that has only got worse since our measurements of stars have gotten better since the 1980s. So much so that the measured Spite plateau of the primordial lithium-hydrogen ratio is around 3 to 4 times lower than what's predicted by Big Bang nucleosynthesis. So that brings me to part 3. What are the possible solutions to the lithium problem? Well, our explanations fall broadly into 3 categories. Either our measurements for how much lithium there is in the universe are wrong, and there's an astrophysical explanation for all of this. Or our predictions from Big Bang nucleosynthesis of how much lithium there should be in the universe is wrong, and there's a nuclear physics explanation for all of this. Or our physics itself is wrong. Maybe there's some new physics beyond the standard model that we've missed. So let's start with the astrophysics solutions. For example, it could be that lithium is actually gradually destroyed in stars' atmospheres over their lifetimes, dragged down towards the very center where it's used up in fusion. And recent detailed simulations from Borisov and collaborators in 2024, which included the proper mixing of elements with convection and turbulence and all the chaos going on inside a star that lead to changes in temperature and what can fuse where, actually showed that the amount of lithium does drop over a star's lifetime. And that happens for all stars, regardless of how much iron this star has, which naturally gives rise to a plateau, like the spike plateau that is consistent with the iron over hydrogen ratio. However, it's not quite enough to explain the difference between the predictions and our measured amount. But is that just a coincidence of the assumptions used in the simulations? How robust are they if you start tweaking with the starting point? So there's still a lot of work to do there. So what about if our measurements are right, but our predictions from Big Bang nucleosynthesis are wrong, and there's just a nuclear physics explanation for all of this? Perhaps there could be extra reactions going on in this cycle that would reduce the amount of lithium made, maybe turning it into heavier elements like carbon and beryllium. But there have been lots of active searches for new reactions, but so far none have been found. But then perhaps the conditions in the early universe are just so drastically different that even reactions that we've been able to make in a lab here on Earth that are possible, that we just don't think are important because it only produces tiny trace amounts compared to other reactions, actually are important because of those different conditions and end up having a big effect on the ratios of the different elements produced. So what about the scenario where our measurements are right and our knowledge of all the reactions taking place are right, but the physics itself is wrong? Perhaps there's something wrong with the standard model of particle physics that underpins all of the Big Bang nucleosynthesis predictions. For example, the standard model currently doesn't have any explanation for dark matter. Matter that we can't see because it doesn't interact with light, but we know is there because of its gravitational pull on objects around it. I have a whole video on the evidence that we have for dark matter if you want to check that out. But despite all of that evidence that us astrophysicists have collected, particle physicists don't have an explanation for what it could be made of, if in fact it is a particle. There is a hypothesis in particle physics called supersymmetry that says all the known particles in the standard model have a supersymmetric partner particle with different spin properties. And that's not just a hypothesis that's popped up out of nowhere. It's been raised to explain things like why gravity is so weak compared to all of the other forces in the universe, and also give a possible candidate for dark matter. And if these dark matter supersymmetric particles were present in the early universe, they could also decay into normal matter particles and interfere in this cycle of reactions that gives us the production of these light elements. Having said that, we have no evidence yet for supersymmetry, despite dedicated searches for these supersymmetric particles in particle accelerators like at CERN. So instead of new particles, what if our fundamental constants of physics could change? Things like the fine structure constant, alpha, which measures the strength of electromagnetic interaction with particles. It's defined by lots of other physics constants you might recognize, including the speed of light, the charge of a proton, Planck's constant, and the electrical permittivity of free space. Perhaps in the first few seconds of the universe's lifetime, the conditions are so extreme that this actually changes the value of these physical constants. Enough to shake up that cycle of reactions and change the Big Bang nucleosynthesis predictions. It might sound crazy, but there have been a lot of observations and lab experiments over the years to try and determine if any of our physical constants do change either in space or in time. Or maybe there's even something wrong with our cosmological model for how the universe has evolved. Specifically what's known as the cosmological principle that I've talked about on this channel before. The assumption that on a big enough scale, the universe is the same everywhere and in all directions. If that's not true, and you do get differences from place to place in the universe, that messes with the ratio between the amount of normal matter to photons, particles of light that you have in different places in the universe. And remember, that's what sets the value of the predictions from Big Bang nucleosynthesis and could give you a different ratio of elements in different places in the universe. So there are many, many different hypotheses that have been raised to solve the lithium problem. Some, admittedly, more likely than others. I think I know which one my money is on, but let me know down in the comments which one you think is the most likely culprit for the lithium problem. Now, I remember when I was starting out in my astrophysics education, how confusing it was to be constantly faced by new scientific ideas that are all interconnected. So if you want to get more familiar with the background science that underpins problems like this, I highly recommend that you check out Brilliant, the sponsor of today's video. Brilliant helps you excel at science, maths, and coding, whether you're 10 years old or 110. I love Brilliant's step-by-step interactive lessons and personalized practice that just gets you to learn by doing, solving problems yourself rather than passively watching lecture videos. The courses are crafted by world-class teachers from the likes of MIT, Harvard, and Stanford, whether you want to learn how to code or just brush up on your math skills or even understand how AI works. I particularly love their data science courses, especially the likes of their Exploring Data Visually course. So much of what we do in astrophysics is interpreting what the plots that we see in research papers are actually telling us. And that is a skill that you can train with Brilliant. So to learn for free on Brilliant for a full 30 days, head to brilliant.org/Dr. Becky or scan the QR code on screen or click on that link in the video description and you'll also get 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. So if you're an adult or you're a kid, check them out. Who knows, it might be the start of your own journey into astrophysics and maybe in the future lead to us finally solving the lithium problem. And it was only recently in the a rainbow, pretty. Sorry. And it was, so easily distracted. Where was I? I don't even know. Oh yeah. Some form of plane or helicopter going over. I did not miss this. Let me see if I can just close the vent on my window. We're back, baby. And that only took me 45 minutes for what, a 15-minute video? We're back, but we're not in practice yet.